Welcome to Cosmos in a Pod Space and Astronomy series, Episode 7. Get ready for a deep dive into the universe's most spectacular light shows. We're talking supernovae, the explosive death of stars, events so bright they can outshine entire galaxies for a short time.
It's really hard to grasp the sheer power of these events. We're talking about a sudden release of energy. It just dwarfs anything we can even imagine creating here on Earth.
I can only imagine. That's mind-blowing. It's like one firework outshining a whole city at night.
Yeah.
So why should we, down here on Earth care about something so far away? Something seemingly unrelated to our lives?
Well, that's where it gets really fascinating. Supernovae. As destructive as they seem, they're actually responsible for creating the elements that make up everything around us, including us. Think about it. The carbon in your cells, the oxygen you breathe, even the iron in your blood. It was all forged in the heart of a star and flung out into the cosmos by a supernova.
So we're all made of stardust. It's amazing. So how does a star go from, calmly burning for billions of years to suddenly exploding with such incredible force?
Well, it's not exactly sudden. There's a build-up to this cosmic grand finale, and the path depends on the type of supernova.
You mentioned different types.
Yeah.
Walk me through them. What's the first one?
The first type, known as a type I supernova, it typically happens in a binary star system, two stars orbiting each other. Now, one of these stars is a white dwarf, basically the dense leftover core of a star that's already run out of fuel. If this white dwarf is close enough to its companion star, it starts pulling material off its neighbor.
Like a cosmic vampire star.
Exactly. Imagine this white dwarf slowly siphoning away material from its companion, growing larger and denser over time. Eventually, it reaches a critical point. It's called the Chandrasekhar limit.
The Chandrasekhar limit. What happens at that point? Is that what triggers the explosion?
Exactly. You can think of this limit like a tipping point. Once the white dwarf exceeds this mass, it becomes unstable. The internal pressure and temperature skyrocket, and it ignites a runaway nuclear reaction that completely obliterates the white dwarf in a blinding flash of light.
So it's like a stellar pressure cooker gone haywire.
Yeah.
You mentioned that astronomers use these type I supernovae for something else, like being a cosmic measuring stick.
You're right. Here's why type I supernovae are so useful. They all explode with nearly the same intrinsic brightness. Think of them like light bulbs of a known wattage. If you have a 100-watt bulb and you see it shining dimly, you know it's far away. If it's super bright, it must be close.
So by comparing the actual brightness of a type I supernova to how bright it appears from Earth, astronomers can calculate its distance.
Precisely. They're called standard candles, and they've been instrumental in helping us map out the distances to faraway galaxies, and even understand how fast the universe is expanding.
That's amazing. A single type of exploding star can tell us so much about the vastness of the universe. So that's type 1. What about the other type of supernova, the one that comes from massive stars?
Ah, yes. Type 2 supernovae. This is the grand finale for stars at least 8 times more massive than our sun. Their story begins with fusion, the heart of what makes a star shine.
Fusion, right. That's where stars combine lighter elements into heavier ones, like building blocks.
Exactly. These massive stars are like giant furnaces, constantly fusing hydrogen into helium in their cores. But eventually, they run out of hydrogen fuel. Then they start fusing helium into carbon, then carbon into oxygen, oxygen into silicon. It's a step-by-step process, building up heavier and heavier elements.
Until they reach iron. You mentioned iron was significant. Why is that?
Iron is the end of the line. It's the most stable element, meaning fusing iron doesn't release energy like the other elements. In fact, it requires energy. So once a massive star's core is filled with iron, it's basically out of fuel, and it can no longer support its own weight. Against the crushing force of gravity...
So what happens then? Does the whole thing just collapse?
It does, and it happens incredibly fast. The core collapses in on itself. The result is an unimaginable shockwave that rips through the star, blasting its outer layers into space with incredible force.
And that's the supernova we see.
That's it, that spectacular explosion, the brilliant light that can outshine an entire galaxy. That's the type 2 supernova.
Okay, so the outer layers of the star are blasted into space.
Yeah.
What happens to the core itself after this dramatic collapse? Is it just gone?
Not necessarily. The fate of the core depends on the original mass of the star. For smaller massive stars, the core gets squeezed into an incredibly dense object called a neutron star. We've talked about those before. They're like giant atomic nuclei just a few miles across, but with the mass of an entire star packed into that tiny space.
Right, neutron stars. Those mind-bogglingly dense objects. But you said it depends on the original mass. What happens to the cores of the really massive stars?
For those truly massive stars, the core's collapse doesn't stop at a neutron star. It keeps collapsing, becoming denser and denser, until it essentially disappears from our universe, forming a black hole.
A black hole. So, depending on its size, the star gets a dramatic exit as either a superdense neutron star or a mysterious black hole. Talk about going out with a bang. But wait, I thought we were talking about how supernovae create things. This all sounds pretty destructive.
You're right, supernovae are incredibly powerful and destructive events, but they're also creators in a sense. Think about all those elements that were forged in the star's core over its lifetime. They get blasted out into space by the supernova. That material enriches the surrounding interstellar medium, seeding it with the building blocks for new stars, new planets, even life itself.
So in a way, these supernovae were like cosmic gardeners, scattering the seeds for new life and new worlds.
That's a great way to put it. Supernovae are essential to the cycle of cosmic evolution, a fundamental part of how the universe works.
Wow, this is fascinating. Are there any specific supernovae that we've actually observed and learned from, like famous ones?
Absolutely. There are quite a few famous supernovae. Take the Crab Nebula, for example. This stunning cloud of gas and dust that formed from a supernova observed by Chinese and Arab astronomers way back in the year 1054.
Wait, they saw a supernova almost 1,000 years ago.
They did. It was so bright it was visible during the daytime for weeks. The Crab Nebula is what's left of that explosion, and it's still expanding today. A beautiful and eerie reminder of the power of these cosmic events.
That's incredible. What other supernovae have astronomers been able to study?
A more recent one, SN 1987A, which happened in 1987, as the name suggests. It occurred in the Large Magellanic Cloud, a nearby galaxy that orbits our own Milky Way.
So it was relatively close to us, astronomically speaking.
Yes, it was the closest supernova observed in modern times, which allowed astronomers to study it in incredible detail. We learned a lot about the physics of supernova explosions and the formation of neutron stars from that event.
I can imagine. But if these supernovae are so rare, how do astronomers even find them in the vastness of space? Do they just happen to look in the right direction at the right time?
That would be incredibly lucky. No, we have much more sophisticated methods these days. Modern telescopes and dedicated sky surveys are key to finding these cosmic explosions, even in distant galaxies.
So what kind of technology are we talking about here?
Well, there's a Hubble Space Telescope, of course,
Oh,
which has captured some incredible images of supernova remnants. And then there are ground-based observatories, like the Vera Rubin Observatory. It'll be coming online soon.
what's special about the Vera Rubin Observatory?
It's designed to scan the entire sky every few nights, looking for any changes, including new supernovae. It's going to revolutionize our understanding of these events.
That's exciting. So it sounds like we have these incredible tools for finding supernovae. But what about studying them? How do astronomers actually learn about what's happening in these explosions?
It all comes down to analyzing the light. When a supernova explodes, it emits light across the entire electromagnetic spectrum, from radio waves to gamma rays. Astronomers use different types of telescopes to capture this light and then break it down into its component wavelengths.
Like a prism splitting sunlight into a rainbow.
Exactly. By studying the patterns in this light, we can learn about the chemical composition of the supernova, its temperature, its speed, even how the explosion itself unfolds.
Wow. It's like they're piecing together a cosmic crime scene, using light as their clues.
That's a great analogy. And with each new supernova we observe, we gain a deeper understanding of these events and their role in the evolution of the universe. It's truly remarkable what we can learn from these distant, fleeting flashes of light.
This has been absolutely fascinating. So glad we're not too close to any of these potential supernovae. It sounds like it would be a pretty rough day on Earth if one went off nearby.
You're telling me. But don't worry. While supernovae are essential to the universe's evolution, we're at a safe distance from any potential candidates in our galactic neighborhood, so we can appreciate their beauty and power from afar.
Glad to hear it. I think it's time for a quick break. But when we come back, we'll continue our supernova exploration with even more cosmic insights. Stay tuned.
Welcome back to Cosmos in a Pod. I hope you're ready for more supernova talk, because we've only just scratched the surface.
I am so ready. You've got me totally hooked on these cosmic fireworks. Before the break, we were talking about how astronomers actually find and study supernovae. It's amazing what they can learn just by analyzing the light. But you also mentioned that supernovae are responsible for creating some of the heavier elements in the universe. Can you elaborate on that?
Absolutely. We talked about how stars fuse lighter elements into heavier ones in their cores, right? Our sun, for example, can produce elements up to carbon and oxygen. But the really heavy elements, think gold, platinum, uranium, those are forged in the intense heat and pressure of supernova explosions.
So that gold necklace I'm wearing, it's actually made of supernova remnants. That's kind of mind-blowing.
You could say that every atom of gold on Earth and everywhere else in the universe was created in a supernova explosion billions of years ago. We literally carry pieces of stars within us.
Wow, that's a powerful thought. So these supernovae are not only responsible for creating the elements we need for life, but also some of the most precious and valuable materials we have. They're like cosmic alchemists, turning stars into gold.
That's a great analogy, and it reminds us that even the most violent and destructive events in the universe can have creative consequences, shaping the world we know. Speaking of those violent events, I have a question for you. Earlier you said that a supernova can briefly outshine an entire galaxy. Just how bright are we talking here?
Yeah, I'm still trying to wrap my head around that.
Yeah.
It's hard to imagine something outshining billions of stars.
Well, to put it into perspective, the energy released by a typical supernova is equivalent to the total energy output of our sun over its entire lifetime. Imagine all the energy our sun will produce over billions of years, released in just a few weeks or months.
Whoa, that's an incredible amount of energy. No wonder they're so bright. But what happens after a supernova fades away? What's left behind?
It depends. As we discussed, a Type 2 supernova, the death of a massive star, can leave behind either a neutron star or a black hole.
Right, the superdense leftovers. Or a cosmic vacuum cleaner. What about Type I supernovae, those white dwarf explosions?
In those cases, there's often nothing left behind. The white dwarf is completely obliterated in the explosion, leaving behind only an expanding cloud of gas and dust.
So it's like the ultimate disappearing act. Poof, gone.
You could say that. But even though the star itself is gone, the material it blasts out into space continues to interact with its surroundings. It can influence the evolution of galaxies, even trigger the formation of new stars.
So even in their death, supernovae contribute to the ongoing cycle of creation and destruction in the universe. It's like a never-ending story.
Exactly. Each supernova leaves behind a unique fingerprint, a story written in the patterns of gas and dust that we can study and learn from. It's like a cosmic echo of a star's life and death.
This is all so fascinating. It makes you appreciate the interconnectedness of everything in the universe. But I have to admit, I still have a lot of questions about supernovae. For example, how often do they actually occur? I mean, are we likely to see one in our lifetime?
Well, supernovae are relatively rare events, at least in our own galaxy. Astronomers estimate that a supernova occurs in the Milky Way, about once every 50 to 100 years.
So we're due for one soon?
Well, soon is a relative term in astronomy, but it's certainly possible that we could witness a supernova in our lifetime.
Wow. I can only imagine what a sight that would be. But you mentioned that we can observe supernovae in other galaxies, right? So even if we don't see one in our own galaxy, we can still study them.
Yes. And thanks to modern telescopes and surveys, we're detecting supernovae in other galaxies all the time. In fact, astronomers discover thousands of supernovae each year.
Thousands? That's incredible. So while they're rare in our own galaxy, they're actually quite common across the universe as a whole.
Exactly. And by studying these distant supernovae, we can learn a great deal about the evolution of stars and galaxies, and even about the fundamental properties of the universe itself.
So each supernova is like a unique window into the distant past, offering clues about the history of the cosmos. It's almost like reading a history book written in starlight.
That's a beautiful way to put it. They're like cosmic time capsules, carrying information about the conditions of the universe billions of years ago.
It's amazing to think that we can access that information from our little planet here on Earth. But we've talked a lot about the scientific aspects of supernovae. What about the cultural impact? Have these events had any influence on human history or mythology?
That's a great question, and the answer is definitely yes. Throughout history, people have been awestruck by the sudden appearance of bright new stars in the sky. Imagine seeing a new, brilliant point of light appear where none was before. Long before we understood what was happening, it must have been a truly awe-inspiring and perhaps even frightening sight.
I can imagine. It makes sense that cultures would incorporate these celestial events into their myths and legends.
Exactly, and they did. Many cultures incorporated supernovae into their stories. For example, in some ancient cultures, supernovae were seen as omens, portending either good or bad fortune.
Oh, like celestial messengers from the gods.
In a way, yes. They were seen as signs from the gods, or as messages from the universe itself. It's a testament to the power of these events, to capture the human imagination.
It seems like supernovae have always had a way of making us look up and wonder about our place in the cosmos,
Yeah.
even when we didn't fully understand what they were.
Absolutely, and even today, with all our scientific knowledge, there's still a sense of wonder and awe when we witness the death of a star and the birth of something new in the universe. It really makes you think about the grand scheme of
I
things.
couldn't agree more. There's something truly poetic about the cycle of life and death, playing out on such a grand scale. It's a reminder that we are all part of something much larger than ourselves.
Well said. And on that note, I think we've covered a lot of ground today, from the science of supernovae to their cultural impact. But before we wrap things up completely, we have one more exciting aspect of supernovae to explore.
You've got my attention. What else is there?
We're going to delve into how these stellar explosions can actually help us understand the universe on an even grander scale. We're talking about cosmology, the study of the origin and evolution of the universe itself.
Ooh, this sounds good. I'm ready to dive even deeper. Welcome back to Cosmos in a Pod. We're wrapping up our deep dive into the fascinating world of supernovae. And I'm ready to hear how these stellar explosions can shed light on the entire universe. You were about to explain how supernovae connect to cosmology, right?
Exactly. It might sound surprising, but these distant, fleeting events can help us understand the universe's biggest secrets, specifically type Ia supernovae, those white dwarf explosions we talked about. They're incredibly valuable tools for cosmologists.
Okay, remind me again, why are Type Ia supernovae so special? You said they were standard candles.
Right, because they all explode with nearly the same intrinsic brightness. We can use them to measure distances across the vastness of space. Think about it this way. If you have two identical light bulbs, but one appears dimmer, you know it must be farther away.
Right. So by knowing the actual brightness of a Type Ia supernova and comparing it to how bright it appears to us, we can figure out how far away it is. But how does that help us understand the universe as a whole?
It's all about the expansion of the universe. Remember, we live in an expanding universe where galaxies are constantly moving away from each other. By observing Type Ia supernovae in distant galaxies, we can not only determine their distances, but also how fast they're moving away from us.
So it's like we have these cosmic mile markers scattered throughout the universe, and by watching how they move, we can trace the history of the universe's expansion.
Exactly. And what's even more amazing is that these observations led to a groundbreaking discovery. The universe's expansion isn't constant, it's actually accelerating.
Wait, accelerating? You mean the galaxies are moving away from each other faster and faster over time? That's wild. What's causing that?
That's the million-dollar question. It leads us to one of the biggest mysteries in modern cosmology: dark energy.
Dark energy. What is that exactly?
It's this hypothetical form of energy that seems to permeate all of space, acting like a sort of anti-gravity, pushing everything apart. We don't know exactly what it is or where it comes from, but it's thought to be responsible for the accelerated expansion of the universe.
So it's like
Yeah.
an invisible force counteracting gravity on a cosmic scale. That's mind-boggling.
It really is. And while we still have a lot to learn about dark energy, its discovery wouldn't have been possible without those distant type Ia supernovae acting as our cosmic guides. They've opened up a whole new realm of exploration in cosmology.
It's incredible how much we've learned about the universe. Just by studying these exploding stars, we've gone from understanding the elements they create to mapping the expansion of the universe. It really highlights the interconnectedness of everything in the cosmos, doesn't it?
It absolutely does. And it underscores the importance of continued scientific exploration and discovery. Who knows what other secrets these cosmic explosions hold, just waiting to be uncovered.
That's a great point. Well, I think that's all the time we have for today. Thank you so much for joining us on this cosmic journey. I hope you learned something new about these incredible events. If you enjoyed this episode, be sure to follow and subscribe to Cosmos in a Pod for more deep dives into the wonders of the universe. Until next time, keep looking up.